Hey everybody, how's it going? So in the last video, we talked about charge, and today we'll be talking about electric fields. And so in the last video, we talked about how if you have a positive and a negative charge, they'll experience some force due to, well, that's a very good spot, I guess. Due to Coulomb interaction, right, we experience the force follows this equation. And so the question we're going to ask here is, how do these charges know about each other? Most forces we've discussed, we have like tension, friction, weight, drag, centripetal force. For the most part, all of these involve some kind of interaction between things, right? The one that's kind of interesting today is weight, because similar to the Coulomb force, we have the Newton's law of gravitation that gives us the force due to gravity between two massive objects. And this is also not a direct interaction between these two things, right? Both of these forces act at a distance, right? So if you have something like tension or friction or drag, like you have to be in contact with two things. And so that's how this is slightly different. And so it's interesting, they both follow the same form and they both kind of have this policy. And you can say both of these act through fields. And so today we're going to talk about the electric field specifically. And so we define the electric field as the force a particle would experience divided by the charge of that particle. So electric field has units of newtons per coulomb. Okay. And so we often use something referred to as a test charge when we're doing this. Sorry, I'm just going to put that there so we have it close by. You can see the force here, force there. If you're looking at the force on one particle from the other, you would replace the Q here with that. And so you could get the electric field due to a particle's KQ over R squared. But we'll get into that a bit in a second. And so sometimes we use a test charge, like if we had one positive charge here with electric field lines pointing out, and we wanted to know the electric field at some point P. Since all the equations we have at our disposal, equation 1 and equation 2, all rely on the charge of some object to begin with, we can say if we imagine a test charge, call this negative Q, we'll have a negative charge, and we want to figure out the electric field at this point P, we can say the force it would feel is equal to K, well, this is positive Q, negative Q squared over R squared. Well, I guess we'll have R, have a direction to it that way. You can find the force, and then you could find the electric field is equal to Fc over negative Q. And so we get KQ over R squared, R hat, for the electric field due to one particle. So for any time you have a problem and you want to examine the role of an electric field in the interaction between charged objects we must first calculate the electric field. Given by a distribution of charge. And then after that, you can calculate the force that the given field exerts on a charge placed in it. And so these are the two different things you can do. You don't necessarily have to do them in this order. In the example we did up here, we calculated the force initially, and then we used that to calculate the electric field. And so we did number 2, then number 1. But there's going to be tons of problems where you start with calculating the electric field, and then you determine the force. It just depends on what you're looking for in a given problem. So as we kind of saw up here, I drew these electric field lines. Let's discuss how those work briefly. So there's, I think, just two rules. First is they point from positive, well, I don't want to, we'll do from positive to negative. I don't want to draw it like a charge because it's just positive things. You know, it can be a sheet of charge, it can be a point particle, it can be a ring of charge, line of charge, which we'll get into that later. But they point from the positive charge to the negative charge. And so if we were to have positive and a negative charge, you would get electric field lines that do something like this. And then if they start coming out the backside, they loop around like that. Cool. And the other rule is the closer together they are, the stronger they are. Right? Which is really easy to visualize if you think of just one particle. If you draw all your lines going straight out, because it's positive, so they go away from it. That's probably enough. You can see if you're very close to the charge, the lines are pretty close to each other, but the further out you go, the further away they are from each other. Meaning that the electric field decays with R, the distance away, which we saw from this equation right here, right? As R increases, the electric field decreases. All right, just like we see here. As R increases, the electric field decreases. Okay. And so next we're going to talk about the electric field due to a dipole. So first, what is a dipole? Dipole is two charges separated a short distance. And so if we have I don't want to do this right here. So if we have a positive and a negative, we'll call this one plus Q and minus Q. And then let's say we want to mark their center, just so we kind of have an origin for the problem. And then we want to find the electric field at some point P. Actually, yeah, let's give ourselves a little space to work. Okay, and so let's pick a color that electric field lines are going to be. Okay, I don't want to do all that. I was really just hoping yellow would be in here. We'll do that for now, whatever. Very fancy. So if we want to look at the electric field line due to positive Q at point P, we can kind of have it pointing in this direction. And I'm going to remove these dashed lines because this is about to be everywhere if we do that. And so we can label this as the electric field from the positive charge. And if we wanted to also look at the electric field from the negative charge, we would have something pointed in the opposite direction with a slightly lower magnitude. So we can call this E minus. And the reason we have a slightly lower magnitude is because we're further away. Right? If we define the dipole separation distance to be D, we can go ahead and say here is R minus, right? The separation of the negative dipole to the point P. And then we could also say we have R plus going from the positive charge to our point P. And so we can see R plus is less than R minus. And so in the equation we have E is equal to K Q over R squared. We can just see off the rip the E plus is going to be greater than E minus, just because R plus is less than R minus. Okay. And so if we want, we can also figure out what the values of R plus and R minus are going to be. And so R plus is going to be so then we also define that P is at, actually we're going to change P to Z. So then R plus is going to be Z minus D over 2, all right, if we're going from here to here. Wait, crap. Okay, yeah. Yeah, if Z is from here to here, and we want to find R plus, which is from here to here, then we would subtract D over 2 to get R plus. Similarly, we can say R minus is equal to Z plus D over 2. Right, this distance R plus here has this distance Z plus this D over 2 getting us there. Okay. And so if we want to figure out E total, we can say it's going to be equal to E plus E minus. So we recall from last semester, this is called superposition. So just like we would have a bunch of forces and we want to find the net force, we add them all together. We have a couple electric fields here. We want to find the net electric field, so we add the two together. And so we can say ET, well, let's keep our vectors here. We're going to look at a scalar for now, and then we'll slap a direction on at the end. And so we have 1 over 4 pi epsilon naught. It's like we'll discuss in class. K is equal to 1 over 4 pi epsilon naught. Sometimes we write the K because we're feeling a little lazy, but if you're trying to be correct, you should write the 4 pi over epsilon naught. Epsilon naught is a constant of the universe that describes how easy it is for electric fields to permeate through a vacuum, and so we have that here. And so then we would have Q over R plus squared, and the electric field for E minus, which if we want, we can go ahead and kind of, E plus is this, plus 1 over 4 pi epsilon naught. Now it's a negative Q over R minus squared. And so what we're going to go ahead and do, just to clean things up a little bit, is put the minus sign there. Okay. And so we can go ahead and start plugging in our values for R plus and R minus. And so if we have R plus, R plus, R minus, R minus. And so we're going to go ahead and plug that all in. Well, we have a 1 over 4 pi epsilon naught everywhere, so I'm just going to factor that out. And then we also have a Q. That's terrible looking. And we also have a Q everywhere. So I guess we'll write it like this just so we can see the factorization real quick. And then we'll go ahead so we had R plus is Z minus D over 2 squared right, where this entire value is just 1 over R plus squared, and then here we have the 1 over R minus squared. Okay. And so we're going to want to simplify this. And we get, oh, my Q. So let's see, what do we want to pull out? If we pull out a one over Z squared, we get 1 over 1 minus d over 2z squared. We're running into trouble here. Okay, that'll fix that. Minus 1 over 1 plus d over 2z squared. We're going to go ahead and move the z out. And so we get the total electric field from a dipole is q over 4 pi epsilon naught z squared. And then we want to find a common denominator for these two. Which gives us Lord. So we multiply both by what? Well, so we'll just do 1 minus d over 2z squared times 1 plus, oh, nope, I lied. 1 plus d over 2z squared over 1 minus d over 2z squared 1 plus d over 2z squared minus 1 minus d over 2z squared times 1 minus d over 2z squared and 1 plus d over 2z squared. Isn't that just beautiful? And so let's try to make this look slightly nicer. ET is equal to q over 4 pi epsilon naught z squared times 1 plus d over z plus d squared over 4z squared minus 1 minus d over z plus d squared over 4z squared. All right, all we did was we FOILed both of these. And then, of course, just like the minus signs there. And so let's see, we have 1. Oh. There was a minus sign out front, which I ignored. So this is positive. That's negative. And so we have 1, we have d squared minus 4z minus d squared minus 4z. And so we have d over z plus d over z. So we have a 2d over z as our numerator. And then let's try to see what the bottom turns into. So we have 1 minus d, well, I don't know why I started it down there. Let's stay in here. I was gonna do it all and then try to simplify it in here, but let's just write with this simplified too. So 2d over z over whatever we get in the denominator. And so we're gonna, God, this is gonna be insane. So these are the same, right? So we combine, and then we're just gonna FOIL one of these. Well, FOIL this, and then see what we get. So we have 1 minus d over z plus d squared over 4z squared times 1 plus d over z plus d squared over 4z squared. Okay, and so let's see what this turns into. We have 1 plus d over z plus d squared over 4z. You know what? In the interest of time, we're just going to say that this reduces to 1 minus d over 2z squared, the quantity squared. Just to keep the video a little briefer than what we could do. And so then we also need, nope. So we're gonna write E, gonna bring this down, Q over 4 pi epsilon naught Z squared. So then we can get rid of this Z and make this Z cubed. And so we get 2QD over 4 pi epsilon naught Z to the third times 1 over 1 minus d over 2z squared squared. Okay. And so then we also take into consideration the fact that z is much greater than d. Scrolling up. All right. Reminder that z is the distance we're looking at, d is the dipole separation. With the idea here being that in general, dipoles are very close to each other. And so if you are far away from a dipole, meaning even a few centimeters from typical dipoles, that z will be much greater than d. And so then we can say d over 2z is much less than 1. And we get essentially this whole term is roughly equal to 1 over 1. Because we have something much less than 1 squared, which is going to make it way less than 1. And then you have 1 minus something much less than 1, which is roughly 1. You have 1 over 1. And we get the electric field from a dipole is roughly equal to, we have the 2 and the 4. So QD over 2 pi epsilon naught Z cubed. All right, and so if you're observing from much further away than dipole separation, this turns out to be true. Okay, and the last thing we're going to look at today is the electric field due to a line of charge. All right. Anyways, just to recap, the actual physics of this problem. Let's go get a different color out. Is we said that the total electric field is going to be the sum of the electric fields from the two individual charges. We figured out what our R values were going to be, how far away we were going to be from the point of interest. And then we just plugged those in. And then we had some messy algebra in there. But as far as the physics goes, you're pretty much done at this point. All right, you've plugged in your relevant values, and you're good to go. All right, you have all your equations. And then this is all just algebra to get to this relatively nice result we can use. And then also another note is sometimes we define P is equal to QD, and this is just called the dipole moment. But we'll see that more as we go on. And so now if we want to talk about the electric field due to a line of charge, or we're going to do a ring of charge. Well, it's a line that's a circle, Right, so let's say we have we'll go light blue. That seems fun. So let's say we have some ring of charge. And we can put a bunch of little plus signs. Right, as you can imagine, it would be cumbersome to go through and deal with each individual charge in a full line. So what we're going to do is define the linear charge density. Right, and for this to be true, it has to be a uniformly distributed line of charge. And we're going to call that lambda. And it has units of coulombs per meter. Charge per length. Right, and so we can do this for if it's a straight line of charge. Say this has some net charge Q, some length L, then we would have lambda is equal to Q over L. Right? If we have a ring of charge like we have here, let's say there's some net charge Q, let's add some radius R, we would say lambda is equal to Q over 2 pi R for the circumference of that circle. Right, so just a little aside, I will say I do realize we just finished talking about waves where lambda was the wavelength. And so now it's the linear charge density. All right, just something to keep in mind going forward. Just like we had K be the spring constant as well as the wave number, sometimes a variable has more than one role, and here lambda is also linear charge density. And that's pretty standard throughout all textbooks. That's not anything unusual that we're doing. So we'll go ahead and clean this up a bit. And so let's, I guess, move this. Yo. Sure. And so let's go ahead and say we want to find the electric field due to this ring of charge at some point P that's a height Z. Oh, we'll move this over to the side a little bit. above the ring. And so we're looking at the center of the ring, and we're going to look directly above at the center. And one of the reasons we're doing this is because we're going to have some symmetry that's going to make our life a whole lot easier. Cool. And so we can say that we want to start looking at just a tiny infinitesimal area of this ring. And we're going to say we're going to look at some value ds, all right? And this is the calculus ds, where it's just an infinitesimal line segment. Well, we'll put arc. Right, but for a line integral or anything like that, it's a line segment. Actually, no, yeah, we're sticking with line. Yeah, just because our line's curved doesn't mean we have to change things, you know? Okay, and so we can say maybe we want to look at some dq. What the hell happened there? All right, just a tiny little tidbit of charge. And we can go ahead and define dq over ds is equal to lambda, all right? So we have infinitesimal charge per infinitesimal length is going to be the same as the total charge per length of this object. All right, and so we can rewrite that if we want as dq is equal to lambda ds, or we can say q is equal to lambda s, right? Which should make sense. We have charge is equal to charge per length times length, right? And so you get charge per length times length, just gives you charge. Cool. Well. Okay. And so if we're looking at that infinitesimal chunk of charge, we can go ahead and say this little chunk of charge is going to have an electric field, right? The point's radially away from it, right? It's a positive charge, the electric field lines point away. And maybe we get some infinitesimal dE. Right, so that's not giving us the total electric field, that's just giving us the infinitesimal amount of the electric field due to the infinitesimal amount of charge in this infinitesimal segment. Cool. And so just like we can say E is equal to 1 over 4 pi epsilon naught Q over R squared, we can say dE is going to be equal to 1 over 4 pi epsilon naught. And now we have dq over r squared, where we have r being the length from dq to our point P. Okay. And so we can go ahead and make this substitution. Where dq is lambda ds over r squared, right? Which is going to potentially come in handy later. It's going to be easier to use geometry to integrate ds than it is to think about how the charge is going to change to integrate dq. So we can rewrite it in terms of ds, and then we have a line integral to do later, and it's going to be a little bit better. Okay. And so we will say this distance here is capital R. And so we can say R squared is equal to R squared plus Z squared. And so we can go ahead and say dE is 1 over 4 pi epsilon naught lambda ds over R squared plus Z squared. With the idea being that R is some given constant. Well, here, let's see. So we have 4 is a constant, pi is a constant, that's a constant. This is going to be a constant given from the problem. So is capital R. And so now the only things that we really have to evaluate is the ds and the Z squared. Right? Z is, the height you're looking at, so that's not part of the ring itself. That's, variable depending on, where you choose to look. All right? Okay. And so, we'll go ahead and get all these arrows out of here. And we're going to go ahead and star this equation because we're going to come back to it. And so let's look at the full ring. We can say dE is equal to dE cosine theta. All right, and let's go through and see how that makes any sense whatsoever. So we picked, let's hop over to this. No, let's do that. Yeah. So we picked our point ds to be over here. But if we picked a different point ds directly opposite, it's going to have an electric field that points in this direction, such that we could say both the horizontal components cancel. And we're only left with some vertical component. Right, and so if we go around in the whole ring, that's going to be true anywhere. For any point we pick, if we pick here, we could go here. If we go here, we could go there. Right, there's always going to be some complementary spot on this ring to cancel out the horizontal component of the electric field and leave us with only a vertical component of our electric field. And so if we were to look at, maybe if we take this and kind of blow it up down here, and so we have our point P, we have DE, and then we're going to get DE cosine theta. I guess we should put like the sum of DE will be pointed in that direction. All right, because if we have this angle as theta, this angle's theta, we can say this is theta, and DE cosine theta, where we now have that defined in our triangle. Okay, and so we can also say cosine theta is equal to, if here's our triangle, we have COA, right? SOCA, we have CA, where cosine is equal to adjacent over hypotenuse, and so we get cosine is equal to Z over R, capital R. Nope, lowercase r. Right, because we have adjacent, hypotenuse, Z over R. Cool. And we've discussed before the lowercase r is related to Z and capital R by Pythagorean theorem. So we can rewrite this as Z over the square root of Z squared plus R squared. And we're going to call this star star. And so if we put together dE equals dE cosine theta along with this, we get dE cosine theta is equal to Z lambda over 4 pi epsilon naught times Z squared plus R squared to the 3/2, because we have the 1/2 from here, and then we have just to the 1 here, and so you get to the 1 times the half, you get to the 3/2, right? Because you add exponents, right? That are multiplied. Okay, and then we also have our ds. Okay. And so then what we're going to do is we're going to say the electric field's equal to the integral of dE cosine theta, right? Basically, we just integrate both sides of this. And we get that is equal to, let's pull our constants out, Z lambda 4 pi epsilon naught and I guess we actually can pull the Z out if we're given a fixed value of Z. And then in other problems, you just plug in what you need because Z is not affected by the ds going around the ring. All right, if ds goes around the ring, Z has nothing to do with that. So that's cool. Z squared plus R squared to the 3/2 and times the integral of ds, and we want to go in a full circle. So we go from 0 to 2 pi r. And if we integrate this, we just get 2 pi r minus 0 is equal to 2 pi r, because the integral of ds is just equal to s. Cool. And so we get E is equal to Z lambda 2 pi r over 4 pi epsilon naught Z squared plus R squared to the 3/2. And let's see what we have up here. Oh, I think I erased it, but we said that if lambda is equal to charge over 2 pi r, charge per length of a circle, then we can say lambda 2 pi r is equal to q. Actually, well, let's do a lowercase q for whatever charge that ring had. And so we can say E is equal to QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2. And for this, since we chose positive charges, if we want to make it a vector, we'd put we would put a Z hat. Why are we doing this? Sure. We put a Z hat on there. Right, because if it's a positive ring, the charges are pointing away. The electric field points this way. That's the positive Z direction. If we had a negative line of charge, then it would just be pointing down towards the ring. And so this is the for ring of charge. And so I know this derivation is crazy. This is probably like one of the first days in this semester where you see like a whole bunch of math on the board. You're like, oh my God, what was that? So just like when we did derivations for single slit and double slit interference, you don't have to be able to do those derivations off the top of your head, the drop of a dime. You should be able to go through this and follow the line of reasoning we use to get to the final equation. But then in the future, if you're ever given a ring of charge and you're asked to find the electric field, you know you can just use this equation. It's in the back of the chapter in the book. Okay. So the textbook also goes through like a uniform disk of charge, where you have sigma is equal to Q over A. If you want to follow along that derivation in the textbook, it's there. They skip a lot of these steps that I did with the algebra, but you're not. I'd recommend looking at it, but it's not something you're ever going to be tested on. All right. Well, have a good one.